Hi class, welcome to exercise 10C, solving exponential equations using logarithms. In this lesson, your examples and pre-learning will be example 6, solving using the giving base. And your pre-learning for this example will be questions 1, 2 and 3 in the new book and questions 4 and 5 in the old book. And then we'll do example 7, solving using base 10. And your pre-learning for this example will be question 4 in the new book and question 6 in the old book. So make sure that you're confident with the techniques that we've learned in the previous 2 classes. In this lesson, we're going to begin to work with applications. So buckle up and we'll see you in the introduction. Now, it might seem obvious to you now, but this lesson is going to be why logarithms are important and useful. Now, the first reason is arithmetic with large numbers. And this is what they used to do before they had calculators everywhere. And that's because log base a of x times y is equal to log base a of x plus log base a of y. And of course, if x is equal to a to the m and y is equal to a to the n, then this sum here is just equal to m plus n. So even though it's obvious when we look at our definitions of x and y at the top right here, we know now that x times y is equal to a to the m plus n, but they would use these facts. They would use what this power was to a certain log base. And there was these tables of values. And so people would use this fact when they didn't have calculators. And I remember Dad telling me about how he would have to look up all these tables for log values all the time. But now that you're born in the lucky age where calculators are everywhere, in fact, you've seen me solve things with my handwriting in OneNote, right? Well, the main reason we use logarithms is to solve exponential equations. And that's because if we have some equation where we got k times a to the t equals x, and you saw equations like this in the exponential section all the time, right? Well, if I divide both sides by k, we've got a to the t equals x divided by k. And because this thing here is just an equation, it's quite legitimate for me to take the log of both sides. So we could now rewrite that as log base a of a to the t equals log base a of x divided by k, because we've just done the same thing to both sides of the equation. And if we look at the left here, we've got log base a of a raised to t. Well, that's just equal to t. And so now we've got t is equal to log base a of x divided by k. And all we did there was use the definition of logs. So as I said, you would have seen equations like this in the exponential block. One example I used in that block was when I asked how long it's going to take for Australia's population to reach 40 million with our current growth rate of 1.6%. So if you remember, we had to use a trial and error method. But assuming that our current population is 25 million, that means that we're going to have 25 times 1 plus 1.6 over 100 raised to the t equals 40. Okay, so that's 25 million times the 1 plus the growth rate equaling 40 million. And when I say times, we're obviously raising it by t for each time step. So let's just clean that up. 1 plus 1 on 6 means we've now got 25 times 1.016 raised to the t equals 40. So this essentially is what we're trying to solve, and that's where the trial and error would kick in. But what I'm going to do now is divide both sides by 25. So we're left with 1.016 raised to the t is equal to 40 on 25, which is 8 on 5, which in decimal notation is 1.6. So if I now take log base 1.016 of both sides, we can rewrite that like this. And the definition of logarithms means our term on the left just becomes t. So the amount of time is when we solve the equation t equals log base 1.016 of 1.6. And let's see if OneNote can sort that out for us. Sure enough, it can. So we've got t is equal to 29.60961. So how much better was that than trial and error? Especially if you're the kind of person who makes as many errors as I do. So yeah, that is a lot easier, obviously. But I can hear some of your brains thinking, what if I don't have a calculator? What if I can't do log base 1.016. Well, never fear. All calculators have log base 10. And if we just attack the problem slightly differently, we'll be able to get to the same result. So let's just say we've got a raised to the power of t equals some x. Then I can take log base 10 of both sides. Now that's equal to t times log base 10 of a equals log base 10 of x, just by using the log law 3. And I can now rewrite that expression as t is equal to log base 10 of x divided by log base 10 of a. And there's absolutely no problem more with doing that, because log base 10 of x and log base 10 of a are just numbers. Okay, so you might see the fancy log writing there, but in reality, once you do the thing on the calculator, it is a number. So going back to what we were doing before, we've already shown that 25 times 1.016 to the t equals 40 when t is equal to 29.60961. But let's try our new method, and let's start at the next step, which is 1.016 to the t equals 1.6. And we found that just by dividing both sides by 25, right? All right, so if I take log base 10 of both sides, we've now got the log base 10 of this 1.016 to the t is equal to the log base 10 of this 1.6. So using our log laws, that's equal to t times log base 10 of 1.06 equals log base 10 of 1.6. And then dividing both sides by log base 10 of 1.016, we get this beast here. However, let's still try that in the OneNote. No, it doesn't seem to recognize my writing here. I'm going to try it one more time. Amazing. I don't understand why it recognized that time and not the other. Anyhow, let's evaluate. Wow, it's 29.60961. 961, I mean. So we still get the same result. So hopefully that makes you super confident in it. But I just want to show you how amazingly accurate this is. Okay, so, and assuming that we're starting on January the 1st of 2020, so we can see we've got 29 years there. So looking at the decimal places and calculating 365 days, 365 times 0.60961 is 222.50765. So it would be that many days into the year 2049. And there's 24 hours in a day. So 24 times 0.50765 is 12.1836. So it'll be that many hours into the 222nd day. And I've just quickly looked that up. The 222nd day will be August the 10th on a non-leap year. And seeing that there's 60 minutes in an hour, 60 times 0.1836 is 11.016 minutes. And 0.16 would be about 1 second. So we'll say it's 11 minutes and 1 second into the 12th hour. So based on our current growth rate, with a current population of 25 million, we expect Australia's population to reach 40 million at approximately 12:11 and 1 second PM on August the 10th, 2049. Is that accurate enough for you? So hopefully you can see where these types of skills can take you. So to make sure that you can really master these skills, let's climb down your ladder of knowledge and make sure we climb to the top. So pause that video now and do the building understanding questions in the new book, which translates to questions 1, 2, and 3 in the old book. And then I'll see you in the next section. Because log base a of a to the t is equal to t by the definition of logs, then if you've got an exponential equation such as a to the t equals x, and you need to solve for t, then you can rewrite that as log base a of a to the t equals log base a of x, because all you've done there is apply log base a to both sides. Then, as we stated earlier, log base a of a to the t is t, so that means that t is equal to log base a of x. And this just becomes a calculator problem. So let's put this into practice with example 6, where we're going to solve the following exponential equations to 3 decimal places. So the first one we got is part A here, where we've got 2 to the x equals 7. And the thing we're focusing on is the base that has the unknown. So we can see that's a 2. So let's take log base 2 of both sides. And by definition, log base 2 of 2 to the x is just x. So now we've got x equals log base 2 of 7. And let's check that out in the calculator. Goodness me, I'm going to have to do that again. And now it works, I don't understand. All right, let's evaluate. And to 3 decimal places, we got 0.8073. So that's 2.807. And that kind of makes sense because 2 to the 3 is 8, right? And that's getting very close to 8. All right, let's move on to part B, where we've got 50 times 1.1 to the x is equal to 100. Now remember, we're trying to solve for the unknown. So to start isolating that, we're going to divide both sides by 50. So we're left with 1.1 to the x equals 2. Okay, 100 divided by 50. And we've got 1.1 raised to the power of the unknown. So let's take a log base 1.1 of both sides. And by definition, log base 1 of 1.1 to the x is x. So we're left with x equals log base 1.1 of 2. And let's check that out in the calculator. What the heck does lambda have to do with anything? All right, I'm going to have to delete that and do it again. One last try. Hurrah! Okay, into 3 decimal places, we've got 7.27, round up the 2 to a 3, so that's 7.273. So obviously 1.1 to the 7.273 is equal to 2. So yeah, just take note that as you saw in part B, we had to divide so that the number that has the exponent we want to solve is on its own. But I still think it's going to be pretty straightforward for you. So pause that video now and do questions 1, 2, and 3 in the new book, or questions 4 and 5 in the old book. And then when you come back, we'll see you in the next section. The method we've just used, where we have a to the t equals x, becomes t equals log base a of x, is very handy. But what if your calculator doesn't have log a, or log base a? Well, never fear, all calculators have log base 10. So what we can do is start, of course, with a to the t equals x, then take the base 10 log of both sides, and I need to fix that up, I should have wrote x, not 10 there. Then log law 3 means we've now got t times log base 10 of a is equal to log base 10 of x. And that means that t is equal to log base 10 of x divided by log base 10 of a. And before you get too nervous about dividing by logs, there's no problem at all because they're both numbers. Okay. All right, enough algebra. Let's get stuck into example 7, where we're going to solve the following exponential equations using base 10 and keeping it to 3 decimal places. Okay, part A has 3 to the x equals 5. So before we go on, you should have a sensible idea of the solution in your head, okay? So 3 to the 1 is 3, so it's going to be greater than 1. And 3 to the 2 is 9, so it's going to be somewhere between 1 and 2. All right, let's keep moving and apply log base 10 to both sides. And using law 3, we can make that as x times log base 10 of 3 equals log base 10 of 5. And that means that x has to equal log base 10 of 5 divided by log base 10 of 3. So let's check that out on the calculator. I don't know why I have to do that twice, but anyhow, here we go. So sure enough, it's between 1 and 2. We've got 1.464. So that's 1.465 when we round it off to 3 decimal places. All right, let's have a go at part B, where we have 1,000 times 0.93 to the x equals 100. So here the first step is to divide both sides by 100. So we've got 0.93 to the x equals 1/10. And now I'm going to apply log base 10 to both sides. And using log law 3, the left hand side there is x times log base 10 of 0.93. And the right hand side, well, we've got 10 to the minus 1. And so therefore log base 10 of 10 to the minus 1 is minus 1. So I can divide both sides by log base 10 of 0.93. And let's see if the calculator will do that one for us. Hurrah. Okay, let's evaluate. And before I do evaluate, notice that they do a lot of little tricks there, but they are answering the question I've put in. So that's around about 31.729. Now just note that I could do that trick with 1 on 10 because it's a power of 10. And don't expect that to happen a lot. And also note again, as I said in the last section, that I had to divide in part B there so that the number with the exponent was on its own. Alright, so right about now you should pause that video and do question 4 in the new book or question 6 in the old book. And then when you come back, we'll be able to summarize this lesson. Alright, so we've arrived at the end of this unit and you should now be able to solve any exponential equation. It's been a huge area of growth this year. And you're going to do more and more with logarithms, and you'll see that you'll be able to change it to any base, not just base 10, but that's for next year. And just generally speaking, the more and more maths that you do and applications of maths, you'll find that logarithms become more and more important. And even though the pre-learning questions and the examples I did weren't heavy on application, I did give you a taste of one in the introduction. So when you're doing your questions in the exercise, make sure you do as many of the applications as you possibly can, because that really is the main focus of this lesson. Okay, we want you to become amazing problem solvers. Alright, so as far as this lesson goes though, a successful student will know how to solve exponential equations by rewriting them in logarithmic form using the given base. Be able to solve an exponential equation using base 10. Be able to use technology to evaluate logarithms. And I really don't know how else you're going to do it for some of the ones that aren't straightforward. But anyhow, well done. You made it to the end of this unit. Make sure you're ready for the end of unit assessment. And I'll see you in the next lesson, whether that's in class or in a video. Bye.